Few persons, even within the industry, realize that the average American uses 23 pounds of copper each year. But even fewer are aware that between 70 and 80% of the copper comes from open pit mines. In other words, shovel dippers, such as this one, will recover about 18 pounds of the 23 pounds of copper you personally will use this year. You'll use those 23 pounds in pennies, in electrical wiring for your new or remodeled home, in your new automobile, and new TV sets, and new telephones, and new radios, and new appliances. Your 23 pounds will be working for you in machine tools of every description and in the armaments and implements of national defense. Copper is a basic part of the good life and a basic metal on which much of our future will be built. Three-fourths of it comes from open pits where tons of material must be moved to recover pounds of metal. Open pit ore contains an average of 1% or less of metal. And open pit mines must blast, load, haul, and dump a pound of overburden and waste for every pound of ore recovered. So the 23 pounds of copper you'll use this year will require the handling of 6,000 to 12,000 pounds of material. Here are the copper-rich mountains of the Southwest. This is the type of terrain which caught the eye of a Captain de la Mar back in 1899 and moved him to assign Daniel C. Jackling, a metallurgist, and Robert C. Gemmell to examine what is now world-famous Bingham Canyon. Here in 1903, first steps were taken to launch the Utah Copper Company and the nation's first open-pit copper mine. Today, it's one of many mines founded on the high-volume handling of low-grade ore. The first power shovel went to work here in 1906. Since that time, this property has yielded more than 2 billion tons of ore and waste in one of the most methodical, low-cost, around-the-clock excavating projects in history. Let's casually inspect half a dozen of the mines which are the grandchildren and great-grandchildren of Bingham Canyon. In the first three, you'll notice that truck haulage is used. In the last three, rail haulage. To a casual observer, these pits have many things in common in spite of differences in arrangement and equipment. There's enough similarity of pattern to suggest that opening a new mine today probably would be a routine procedure. Not so. While today's mine executive has more technological information than ever before, this same information serves to warn him of what he's up against. The earliest pits were, of necessity, almost completely experimental. But as costly lessons were learned the hard way, mine executives staffed their organizations with scientists and equipped them with specialized tools to convert every phase of open pit mining from a guessing game to a scientifically based industry. A small fortune has been invested in a long-range plan for each of these properties. The studies and projections required by today's mine executive before he'll commit men, money, and machinery to a new pit actually unfold for him the complete story of that mine's operation and production for the next 3 decades. For example, geologists must provide detailed word pictures of all information that has a bearing on the production of the property. It is the geologist who composes technical descriptions of ore bodies, such as this actual description of a mine. Quote, "It lies in a mineralized zone belted on the east, west, and north by well-defined faults. The ore body consists principally of schist, with intrusions of quartz porphyry and diabase. The dominant ore mineral in the schists and quartz porphyry is chalcocite, with some native copper, and in most areas has been heavily oxidized. In the diabase, the dominant ore mineral is chalcopyrite. The ore disposition in the schist portion of the ore body is very erratic, with no apparent structural explanation." End of quotation. Geologists are just one of many groups of specialists who are accumulating newer and better information to help guide the future of mine expansions and the location and development of new ones. Thus, in an industry which is little more than half a century old, it's possible to compare the pioneers with two-fisted gamblers who played their hunches and fortunately were able to guess right more often than wrong. In contrast, today's mining executive brings his technicians and his electronic computer to the gaming table, greatly reducing his risks. If you own the property you're now viewing, you could use many techniques to help evaluate its worth. You might use three-dimension aerial color photographs, which, by the use of unusual films, filters, and developing methods, can help locate ore deposits that escape the human eye. Or you could use any one of several other methods to determine the best locations for exploratory diamond drilling or core drilling, shown here. Core samples help geologists and geophysicists develop an accurate map of the ore body. Typical of the unusual methods used to select core drilling sites is the technique used recently in British Columbia. There, the property was almost completely covered by grass range and woodlands. A resourceful exploration team used a combination of rubianic acid soil testing and magnetometer readings to select the best diamond drilling locations in a 7,500-acre area. Today, core drilling is being pushed to greater depths than ever before. Techniques have been developed to deal successfully with such earlier problems as deep drilling and badly fractured ground. Many lessons have been borrowed from oil drilling, such as highly resourceful use of mud and quick-setting cements. Today's exploration programs make use of such devices as helicopters to deliver men and equipment to remote locations that previously were inaccessible. A fantastic engineering workload precedes the development of any mine, and exciting new developments are underway to increase the speed and efficiency of the engineering effort. In one mine, aerial survey methods provide a complete map in 1 month's time, which previously required 6 months of work by transit and chain gang methods. Another example is the use of digital computers. Although computer rental amounts to $6 per minute, its use is credited with reducing the cost of calculating a strata shot by nearly 2/3 and cutting traverse station calculations even more dramatically. Surveying drill hole costs were cut to 1/3 by the use of a computer. Greater accuracy is another benefit. There have been impressive advancements in the engineering control over the cutoff percentage between ore and waste. Engineers can break down bench bank sections into individual analyses to guide foremen in positioning shovels to mine ore or waste as required. When the exploration and preliminary engineering studies for a new mine have been completed, stripping equipment usually gets the first call to action. Here you see a new mine opened in 1959 that requires the stripping of 200 feet of alluvium waste, which is being removed at the rate of 2,500,000 tons a month by 4 9-yard shovels and a fleet of 55-ton trucks. More than 45 million tons of overburden must be removed to expose the ore body. In opening 2 50-foot benches, tests proved that light blasting ahead of the shovels substantially increased their efficiency. Open pit mining calls for many special skills. One of the most demanding is concerned with blast hole drilling. So many factors have contributed to the various drilling methods and patterns used in different mines that it's almost impossible to generalize, except that every mine, without exception, is constantly seeking better, faster, and less costly methods. The advent of rotary drills established a new general pattern that virtually outmoded churn drills and other slower methods used of necessity in the earlier years of open pit mining. Electric rotary drills from 6-inch to 12-inch sizes are in general use, depending on the nature of the material, the width of benches, height of walls, and the pattern of fracturing required for efficient operation. A typical 9-inch rotary drill will average 650 feet per machine shift, depending on the material being drilled. For pioneer drilling, diesel drills and pneumatic rotary drills are widely used. Benches in various mines range from 35 to 55 feet in height, and the floor of the bench can range from 80 to 120 feet. Maintaining established bench patterns requires skill and experience in the size, spacing, and placement of blast holes. One mine has developed, through experiment, a pattern of drilling at a 70-degree angle, an example of the variations to be found in drilling practices. It's a general practice to drill 5 to 8 feet below grade, but each mine has its own individual blasting personality, which must be understood through experience. For example, some mines use a combination of 3-inch down holes and toe holes. Explosives are a lively subject in open pit mining. both because of the important job they do, because of their cost, and because of the tight network of safety regulations surrounding their use. Ammonium nitrate is a common sight around any open pit operation. In a typical blast area, the drillers have finished their work and moved on. The explosives crew is ready to take over. The blasting hour is not far away, for seldom are explosives left in the ground, even overnight. Many types of detonating devices are used, but there's a definite trend toward commercial detonators, which provide a better safety factor. Some are impervious to both water and to rifle bullets, but respond without fail to the action of the primacord buried inside the detonator. Explosives go into the blast holes at a rate of approximately 10 pounds per foot of hole depth. Thus, a 36-foot hole gets an average charge of about 360 pounds. In the background, drill cuttings or mill tailings are being stemmed back into the holes on top of the explosives to direct the blast force to useful work. Field mixed explosives beginning in 1954 have grown in popularity in open pit mines and today account for a big percentage of the commercial blasting agents used. Here, ammonium nitrate and fuel oil are being introduced into the blast hole together. They are used in measured amounts, and as the ammonium nitrate absorbs the fuel oil, they form an effective and relatively inexpensive blasting agent. A wide variety of transporting and blast hole charging equipment is in use today, including costly special trucks which pre-mix the ingredients and force it into the holes. Some mines prefer to mix their ammonium nitrate and fuel oil under controlled conditions in a slurry preparation plant. The ingredients are combined, mixed thoroughly, and bagged, often in transparent plastic containers which are watertight. In general, the methods of receiving, storing, handling, and hole loading explosives varies with individual mine experiences with regard to costs, safety, convenience, and effectiveness. The stemming operation to plug the drill hole follows a fairly consistent pattern. Drill cuttings are packed down on top of the explosives to assure the horizontal explosive push that will fracture the bank in the desired pattern. When blast time comes, the answers to many hours of preparatory work come quickly. In most mines, there are few surprises, for the blasting pattern has been carefully controlled by experience. However, interested eyes are watching the scene for clouds of a brownish red color, which would indicate the blast efficiency was not as great as it should be. The pattern of fracturing is another clue to the success of the shot as soon as the dust settles. Periodically, individual mines will make special studies of blasts in which slow-motion movies will be taken to permit study of the pattern of burning. Out of such studies can come experiments in changing the mix, tests of different commercial grades of ammonium nitrate, the use of larger blast holes, the use of gelatins and other techniques to deal with holes partially filled with water, or even a decision to turn the blasting problem over to outside blasting service firms, which are now prepared to handle this responsibility on a contract basis. Blasting has a direct relationship to production and even to equipment maintenance. As a result, the blasting program seeks definite and precise degrees of fragmentation. Extremely difficult blasting problems arise in areas where block caving and underground mining methods have been used in the past. Open pit techniques make it possible to reopen such properties on a sound basis, but many special blasting problems are involved. After the blast, there's the cleanup work, secondary blasting, and toe hole blasting to be done. Large rocks too big for the crusher are set aside by the shovel for jackhammer drilling and secondary blasting. Dozers move in to clean up the haul roads and get the bank ready for the shovel. Toe hole drilling, usually handled by a crawler, mount, and liner, is necessary to even up the face of the bench. Some mines use rubber-tired toe hole drills for ease and speed of handling. When fracturing patterns chronically leave large rocks requiring secondary drilling and blasting, cage drills have proved to be a fast, versatile solution to the problem. These flexible rigs are controlled completely by a single operator in a boom-supported cage. He can propel and steer the unit into the desired position, raise and lower the boom supporting his cage, move the cage along the length of the boom, and operate the drill. This equipment permits them to reach and blast large rocks without waiting for the shovel to set them aside for drilling with conventional jackhammer equipment. Meanwhile, there's bench trimming work to be done on the bank following the blast in the interest of safety of both men and equipment. Drag-type trimmers and truck-mounted units with a bucket mounted on a stiff arm are among the types of equipment used to dislodge loose material and trim the bank. Loading and hauling receive more attention than any other subject in open pit mining. The reasons are obvious. Here are the big items of capital and operating expenditures. Here also are the pieces of equipment that exert major control over production and unit costs. This 4.5-yard shovel used in pioneer and utility work is one of the smallest sizes in general use because larger shovel dipper and truck sizes will yield lower unit costs in situations suited to the use of larger equipment. This 6-yard extra heavy-duty loading shovel was designed to work continuously for many years in some of the world's hardest digging. Ward Leonard electric controls in combination with electrical exciter units give this type of machine a combination of built-in shock protection for both electrical and mechanical assemblies without any sacrifice of operating speed. Even greater machine responsiveness, dependability, and operating economy is being developed through the use of new static power amplifiers. Notice that the machine's crawlers are at right angles to the bank. This permits loading into trucks, which are alternately spotted at the right and the left of the shovel. Shovels of 6-yard capacity and larger require 35-ton to 55-ton sizes of truck equipment for efficient operation. Together, they'll produce from 3,500 to 6,500 tons per shift, depending on the rock conditions. Each mine has special haulage distance and grade problems that have a bearing on the size of truck equipment. Where selective mining is required, it's sometimes more economical to consider smaller loading and hauling equipment. Crusher size also has a bearing on the optimum capacities of related equipment. Loading and hauling overburden and waste is a problem that varies from mine to mine and is solved in a variety of interesting patterns. The distances and grades involved in disposing of the waste, plus the need to keep haulage equipment available to the 6-yard shovel, such as the one shown here, call for resourceful planning. For example, in this mine, trucks haul the waste to a big rail loading dock and trains complete the disposal job. Obviously, the waste and overburden disposal problem is aggravated when the material must be moved upgrade from the loading area before it can be dumped. If the mine is fortunate enough to have a large ravine nearby, the waste disposal problem is greatly simplified. Dozer equipment keeps the dumping area in condition for trucks to dump their loads into the valley below without the need for any rehandling. In some situations where the nature of the overburden permits, rippers and scrapers are used in stripping. Open pit mining, however, has virtually exhausted the easy pickings and is now obliged to move progressively more overburden and waste to reach new ore bodies. Here is where the pressure for bigger shovels and bigger trucks becomes the greatest, for low unit costs are imperative. That's why you'll find equipment such as 13-yard shovels and 55-ton trucks teamed on projects that require around 1,200 yards of output per hour for economically sound development. These bigger loading and hauling units cast big shadows of things to come in the years ahead, for they represent one of the relatively few areas in which significant reductions in unit costs are likely to be achieved. The shovels of the future are available today, and they've proved they can do their part of the job. These new efficiencies in stripping are being explored both by mining companies and large contracting firms, which handle stripping work for the mines on a contract basis. The bigger trucks needed to develop the potentials of larger shovels are already in the field testing stages, and in some instances, they're at work in the pits. Some of the newer truck designs employ the motorized wheel principle that has revolutionized the design of railroad locomotives. Each wheel becomes an electric motor powered by the vehicle's own diesel generator. An incidental but significant advantage of the motorized wheel is powerful frictionless braking. The driver simply reverses the polarity of the individual wheel motors to obtain braking action. Trucks of 75-ton, 90-ton, and 110-ton capacities are already in sight. They're certain to have a profound effect on the loading, hauling patterns of the future in open pit mines. Here is one prototype of the electric wheel truck that climbs a 14 to 15% grade at 12 miles an hour with a 60 to 70-ton load by using a trolley for supplemental power. Under its own diesel-generated power, it can operate at 8 to 9 miles an hour over grades up to 6%. When operating on trolley wires, each wheel delivers 400 horsepower, or a total of 1,600 horsepower for the 4 wheels. When operating on its diesel generator, it has about 350 horsepower. Every dimension is impressive. For example, the tires are nearly 7.5 feet high and 4 feet wide. One of the many types and sizes of trucks undergoing tests in mines is this lightweight model, especially designed for increased speeds on relatively steep grades. Air suspension is among its unusual features. Mine executives are encouraging the development of newer and better truck haulage equipment with dramatic results. Here, a 13-yard shovel loads a conventional large diesel truck, typical of those in general use today. Now watch a new monster truck being loaded by the same shovel. From 7 to 9 passes of this 13-yard shovel are required to load it. This motorized monster uses 2 diesel engines with a total of 850 horsepower and can carry a 150-ton payload. It travels on 18 tires, size 1800 by 33, each of them 32 ply, and has a loaded weight of nearly 300 tons. Such a truck dwarfs conventional equipment, but the economics of open pit mining make it almost certain that such new concepts of loading and hauling equipment are on the way. How to haul big payloads up steeper grades as pit problems increase, and how to reduce unit costs from the pit to the crusher are problems which are certain to get continuing big-scale attention in the years ahead. Truck haulage calls for a network of roads that must be kept in good condition. This grader and water truck are typical of the equipment and programs developed for haul road maintenance. The big reason for this emphasis is the cost of tires. They represent 1/3 of all haulage costs, and in some mines, tires represent 1/9 of total costs. The big enemies of these costly tires are rock cuts, breaks in casings, and heat. Combine these with the ever-present dust problem, and you can begin to understand why paving and maintenance of haul roads gets careful attention. Some pits, especially those in dry areas, find it worthwhile to use asphalt paving on main haulage roads, recovering the costs in tire savings and the reduction of dust. Many pits which find asphalt too costly and the use of either plain water or calcium chloride not sufficiently effective are turning to lignin sulfonate, a byproduct of the manufacture of paper. This chemical, applied as a 10% solution with ordinary sprinkling equipment, such as a tank truck, binds dust to the roadway and forms a hard, rock-like surface. Its use saves millions of gallons of costly water per year, brings about dust reductions up to 90%, and cuts costs up to 1/2 as compared with sprinkling. The paved surface it produces is self-healing after a rain, and occasional light applications renew the paving bond. Even though trucks have had a profound effect on open pit mining and have literally made possible a 100% increase in production, rail haulage, as shown in these loading scenes, continues in general use. Especially where the grades are gradual and long hauling is involved, rail equipment will continue to be written into mine development programs. Control towers, such as this one, permit radio direction of train movements to keep empty cars under busy shovels. Shovels are widely used for loading. Shovel sizes, in general, range from 6 to 9 yards, loading rail cars that range in capacity from 60 to 125 tons. Standard gauge rails are used, varying from 90 pounds for bench haulage to 132 pounds for main haulage. Many factors affect the selection of the locomotive equipment. Some mines use trolley power, others use a combination of diesel power and electric trolleys, while still others are 100% diesel electric. Engine power varies from 1,000 to 1,800 horsepower. In mines where more than one size of equipment is used, the smaller cars generally are used for ore, and the larger equipment handles the waste and stripping. In rail haulage, the loading range is critical, and the shovel travels parallel to the bench and rails to help stabilize the range. Notice here that the shovel is equipped with dual cabs for operator safety and improved visibility regardless of the direction of work. These scenes show loading shovels that are typical of the gradual trend toward larger equipment. Shovels use from 2,300 volt to 5,000 volt electric power sources, adapting this power through motor generator sets and highly developed control systems that give operators instantaneous response to easy operating levers and switches at the control station. Most control systems automatically protect the loading machinery against shock overload. Some shovels are equipped with sprinkling systems to help minimize the dust problem. Hard, abrasive materials in a wide range of sizes and the constant possibility of encountering hidden boulders make this work some of the hardest digging on Earth. Developing materials that can give long, dependable service is a constant challenge. Manganese steel and T1 steel are widely used in dippers, and constant tests are underway to improve dipper teeth, cable, and other high mortality parts and equipment. The end of the line for the ore loading and hauling operation is the crusher, usually a gyratory type in sizes up to 60 inches. This is a typical rail dumping point to feed a crusher at the mill site. But for almost every ton of ore, another ton of waste and spoil must be handled. These scenes show a typical rail waste dump, with the cars unloading in a pattern that will keep the waste evenly spread. Periodic track relocation is required to maintain efficient disposal of the waste material. As shown in these views, a grader is needed to keep the waste pushed over the bank to make way for the next series of dump cars. Mile for mile, rail tracks in open pit mines carry hundreds of times more traffic than the nation's railroads. At one mine, an average month's traffic amounts to nearly 66,000 gross tons per mile of installed track, a figure 880 times greater than the corresponding tonnage for the nation's biggest freight hauling railroad. Much of a mine's mainline trackage is built on continuously settling fill, adding a further complication to the heavy problems of track maintenance. The need to relocate tracks almost constantly and the necessity to raise tracks 2 or 3 times a year because of settling make it imperative for large mines to mechanize track maintenance in many different ways. Ballast packing equipment does a faster and more uniform job than hand labor. A ballast regulator dresses the ballast section, blading the material to the top of the ties and sloping the shoulders. Track sweepers clear surplus ballast away from the rails and help guard against shorts in the railway signal systems in wet weather. Track moving problems are handled by a variety of methods, one of which involves the use of a bulldozer equipped with a winch. One type of equipment grasps the section of track on which it is resting and moves both the track and itself in the desired direction. If necessary, a dozer can use its blade to relocate the track. Sectional or panel handling makes use of a rail-mounted crane as shown here. Sections of track satisfactory for reuse are swung into position on a prepared track site. Crews working with the crane bolt the panels together. The crews and crane move forward to repeat these steps until the track is completed. Track work is more precise than it might appear. Grades are held to about 3% maximum, and curves have a maximum of approximately 33 degrees. Straightening bent rails is a big enough operation in at least 2 mines to justify the development of this special hydraulic equipment. From a central control station, the operator moves bent rails from a storage area to the straightening device. Each rail is positioned for a series of hydraulic ram thrusts, and when it's been straightened, it's moved to a storage rack for reuse. Skip hoists are typical of special equipment used by mines to solve special problems. In these scenes, a skip hoist is providing a fast, efficient, and economical means of getting ore out of a relatively deep, small pit. 22-ton skips, powered by 4 500-horsepower electric motors, selectively dump waste or ore into 200-ton receiving bins. The hoist operator controls the complete operation from a station near the head frame. 2 sets of safety devices automatically prevent overspeeding, over-travel, reverse travel, brake malfunction, and clutch engagement. The projected savings of 6 cents a ton indicated in studies comparing the skip hoist with other methods of handling is expected to amortize the equipment investment in less than a year. Here's another pit where 25-ton skips travel a 1,200-foot trackway. This mine credits the skip hoist with a 50% reduction in the truck fleet required to serve the pit. Skips are loaded by a drive-over structure containing 2 25-ton surge bins, which permit truck dumping and skip loading as independent operations. This view shows where preliminary grading has been started for still another skip hoist installation. No tour of open pit copper mining is complete without a visit to leeching ponds. These usually are built in waste that has been dumped into a ravine. If the ore lacks sulfide, it's necessary to add acid to the water. Water pumped into the ponds percolates through the dumped material, oxidizing sulfides and dissolving sulfates and soluble copper. Water that is percolated through a dump will contain 16 or more pounds of copper per 1,000 gallons. The water goes to concrete precipitation tanks, where scrap tin cans collect the copper from the solution. The copper is removed from the scrap by a high-pressure jet of water and is then removed from the tank for drying and smelting. One mine's recovery of copper by these methods justifies extensive stainless steel pumps and related equipment and a full-time crew of 15 men. Open pit copper mining companies are fully aware of the importance of good equipment maintenance practices, as proved by the scope of their facilities and maintenance programs. All mines have shops equipped for machine work, and their warehouses keep on hand a variety of essential replacement parts. Carefully developed inventory programs keep supplies of parts at a practical minimum because the mines rely on suppliers for prompt parts service. Some mines use IBM and other semi-automatic inventory control systems. Truck haulage pits usually have their own shops to provide 24-hour and 48-hour services such as refueling, lubrication, tire care, and inspection to determine the need for major service work. A central shop handles such major works as engine and transmission overhaul. These centers are fully equipped for the heavy, complicated work involved. Detailed records give owners the information they need to develop unit costs on the operation and upkeep of equipment. This information is vital to the constant testing of new types and sizes. Shops equipped to maintain rail haulage equipment contain machine tools essential to the repair and rebuilding of rail car trucks, wheels, bodies, and dumping mechanism. Shovel dippers, clamshell buckets, crowd racking, and other wearing parts in loading units are serviced in well-equipped shops. Equipment too big to come to the shop is serviced in the field. Some mines use color coding on service vehicles to identify electrical, mechanical, and engineering department equipment. Many service vehicles are equipped with two-way radio. Here, a crane unloads a shovel part for installation in the field. Cranes, trucks, men, and tools are equipped for every possible type of service work. These mine service and maintenance people have an important voice in the research programs of most major suppliers, and they help hasten the development of more dependable, more easily serviced equipment that can cut unit costs in the years ahead. You've seen how the fires of research and technological progress are burning brightly in every area of open pit copper mine development and operation. But the hottest flame of all is not in the pits, but in the marketplaces of the world. The copper industry is researching, as never before, all of the many new uses for its metal in such areas as atomic submarines, for which it is already supplying vital components, and many other phases of nuclear fuel and energy applications. There are new uses for copper in the exploding world of computers and other electronic miracles, as well as new uses for copper in your future dream home, the automobile in your future, the planes, trains, and ships of future decades, and in every field of industrial development, including automation. What will your personal copper requirements be 10 years from now? Will today's average of 23 pounds be doubled or possibly tripled? Whatever you will want or need, you will get. For here is an industry that lives in the front line of progress, with an eye on your future needs, and is capable of filling your requirements to overflowing.